Hey folks, this is a lesson on how you predict a precipitate using Q or reaction quotient, or sometimes we refer to it as our trial ion product. So if you have an equilibrium, like the one shown here where you have the solid dissociating into its two ions, we know that at equilibrium, when we have a saturated solution, that the concentration of the product A times concentration of B will equal the KSP, right? And that happens when you have a saturated solution. Now, if the solution were to be unsaturated, right, that's a scenario where no precipitate would form. And that happens when those two concentrations, their product is less than the KSP. So by doing a comparison to KSP, we can predict whether precipitate will occur, because if the concentration of A plus ion times B minus ion is greater than KSP, like we see here, we get a supersaturated solution. And it's a supersaturated solution where we end up getting our precipitate, right? So that's where we're going to see some solid form. Now, the interesting thing about this is when you have your solid, right, you're sitting there and you've got your container in solution, those ions are going to come out, right? And you're going to get your precipitate form at the bottom. But that's going to, when that occurs, it'll stop precipitating when the A minus concentration times the B minus concentration, A plus times B minus, when that equals KSP, then we stop precipitating, right? So in that scenario, precipitation would stop. So once that occurs, right, then our precipitation stops. And we won't see any more solid form. But once we're above it, so that precipitation would only occur when our ion concentrations, the product of those ion concentrations, is greater than KSP. So we can use this information just to help us out here if we want to understand whether or not a precipitate might form, and that's where we use something called a reaction quotient. Now, a common source of a precipitate in our everyday lives is just in our tap water. Tap water has really low concentrations of a lot of different ions, but two of those ions, if the concentration becomes high enough, can start to precipitate. So calcium and carbonate are both ions found in tap water in really low concentrations. So water just keeps flowing, no problem. But when we use something like a kettle, I don't know if you've ever looked inside a kettle, but inside your kettle you likely have some white crusty buildup, or sometimes on your shower head you get a crusty buildup near the little outlets where the water come out, right? That crusty buildup is calcium carbonate. It's just solidified. And because that happens because in the kettle where you're heating it, right, that water's getting really hot, it's starting to boil. So what happens is those ions don't boil, they stay there. So the concentration of the ions gets higher and higher by that element as that thing is heating. And as that concentration gets higher and higher, it reaches a point where their product of the ion concentrations becomes greater than KSP, and then that is when we see it precipitate and we get that white solid form. On your shower head, that happens because as the water that's sitting there dripping out when you turn off the shower, it's still wet, so there's still ions present in that water. When that water starts to evaporate, the ions have nowhere to go. Their concentration is going to get high enough that all of a sudden they're going to precipitate and you're going to be left with that white crusty stuff. So we can compare, if we can look at the ion concentrations, we can determine by comparing their product at whatever concentration you're at. You might not be at equilibrium, but we can look and see if we have these concentrations, is that enough that if this were at equilibrium, would a precipitate occur? And that's where reaction quotient Q, or sometimes, like I said, we call it our trial ion product, that's where that can come into play. So here's how we do it. Q is set up the exact same way as KSP, right? Same setup. As KSP, but uses initial concentrations, right? Because we don't know if they're equilibrium at that point. We don't know. So we put in our concentrations that we know at that particular time, and we use that to compare to KSP. So if the Q value is equal to the KSP, then we know that that would be a saturated solution and no precipitate would form, right? If the Q is less than KSP, then we know it's unsaturated and no precipitate forms. So the only time we get a precipitate is this time right here when Q is larger than KSP. That scenario happens when you have a saturated solution, and with a saturated solution, a precipitate can form. So we're going to take a look at these and try two little problems here. So the first problem involves a solid and another solid being added to water. Now, we've already given to you in moles, so it's pretty straightforward. Now, it could be given to you mass. You would have to convert to moles and then find a concentration. But if we're adding this 10 liters of water, we're going to make the assumption that adding this quantity of moles isn't changing the volume. So we can just figure out what is the concentration of things that are in here. Now, what is good to do in a problem like this is to look at each particular reaction, because I know from this, I want to figure out is a precipitate going to form, and that precipitate is Ag2S. So I need to look at where does the Ag come from and where does the S come from. So the Ag comes from the silver nitrate. So I want to figure out the silver ion concentration, right? That's what I'm going to try and find. So I'm going to do that. I know that AgNO3, if we remember our dissociations, I know that this is going to dissociate into silver ions and nitrate ions, and it's a 1-to-1 ratio. So I know if I have the same number of moles, therefore moles of Ag has to equal moles of AgNO3. Right? So that ion, the silver ion moles, has to equal the silver nitrate moles, so I can find concentration. So our concentration of silver ions, you could use C if you want, I'm just going to use concentration of the brackets, is moles divided by volume, right? So I can say 1 times 10 to the negative 6 divided by 10, that is 1 times 10 to the negative 7, and that now is a concentration of moles per liter, and so that's how many silver ions are, as a concentration, are in this container. Right? The next thing I want to do is find the sulfide, because I know the sulfide is the other piece that I need. So again, I'm going to look at how this dissociates. Na2S, if I put it in water, is going to dissociate into sodium ions and sulfide ions. And I know there's 2 sodium ions based on how that balances, but the sodium isn't really what I'm worried about, it's the sulfide. So I know the ratio is 1-to-1 between sodium sulfide and the sulfide ion. So the number of moles of sulfide ions has to equal the number of moles of the Na2S. Right? So then I can find the sulfide ion concentration by just doing N over V again. So this is 5 times 10 to the negative 4. And I'm going to divide that by 10. So that's just going to be 5 times 10 to the negative 5 moles per liter. So now that I have that, right, I have those ion concentrations, I can now use that to find Q, right? So that's the first part. And I'm just going to grab my calculator because, that could be useful. All right, so to find Q, right, so this is now where we're going to deal with the equilibrium. So we have Ag2S, solid. This is an insoluble salt, so it sets up our equilibrium. We get 2 silver ions and 1 sulfide ion in this equilibrium, which is important because when we set up Q, our Q is going to be equal the same setup as our KSP. So it's silver ion concentration squared times sulfide ion concentration. Now, what you'll notice is I don't need to take the concentration of silver ions and multiply by 2 because of the ratio. The silver ions is coming from what I put in the container, so I can't change that. The silver ions in this scenario are not coming from the dissociation of this. We're kind of working backwards to see if this dissociation would occur. So what went in the container was this amount of silver ions. What went in the container was this amount of sulfide ions. So I am literally just plugging that information into Q. So my silver ion concentration is 1 times 10 to the negative 7, and that quantity is squared, and 5 times 10 to the negative 5 for my sulfide ion concentration, and then I just do the math to find Q. So I'm going to plug it in my calculator 1 times 10 to the negative 7. If you can't see me, I've got my calculator. That quantity is squared times 5 10 to the negative 5. And I got 5 times 10 to the negative 19. Right? So that's my Q value. And now, in order to tell if a precipitate occurs, right, because that's the goal here, to figure out if precipitate, I want to compare that to the KSP and see which is larger, right? And so if I compare 5 times 10 to the negative 19 versus 8.8 times 10 to the negative 18, the KSP is larger. So since Q is less than KSP, no precipitate. So even though we're mixing two substances in there that should form a precipitate because the product is insoluble when those things combine, their concentrations aren't high enough, we're likely not going to see a precipitate. So that's how we deal with two solids. Now let's look at a scenario where we are dealing with two solutions, right? So in this case, the only real difference now is we kind of have to deal with the fact that when you mix two solutions, you're actually diluting stuff. So to figure out initial concentrations, it's not necessarily what that chemical concentration provided to us in the question is. So again, I'm going to look and say, okay, what's my possible precipitate? Now, they kindly give us the KSP of barium carbonate, so that kind of clues us in, that's a precipitate. But if you're not sure, you could always set up the double displacement reaction. So I'll show you what that looks like. So if I were to take barium nitrate, BaO32, take that and set up my double displacement, which sodium carbonate, Na2CO3. In the double displacement reaction, this would produce barium carbonate, and according to the solubility rules, that's insoluble. And then I would also produce sodium nitrate, right? And if I want that balanced, I need a 2 there. So this, if you don't know, if let's say they don't tell you the KSP value, you had to go look it up in some chart somewhere, we could just set up the double displacement to figure out what the insoluble product is, and then I know what I need to work with to find Q. But, as I said, since they gave us barium carbonate as the KSP value, that's likely the thing that we need to find. So I really need to figure out what's the barium ion concentration and what's the carbonate ion concentration. So I'm going to look at where those come from. The barium is in the barium nitrate, so let's start with that. Find barium 2+ concentration. That's my first task. So to do this, I'm going to use the barium nitrate. I know that according to this barium carbonate, right, that barium carbonate, actually it's barium nitrate, sorry, barium nitrate would dissociate into barium ions and 2 nitrate ions. And I'm just doing this because I want to make sure I have the right mole ratio, right? So I know that based on the mole ratio that the concentration of barium ions should be equal to the concentration of barium nitrate because it's a 1-to-1 ratio, right? So because I have that information, that makes this a little more useful to me. Now I just have to consider the fact that I took 20 mils of this solution and added it to 80 mils of the other solution. So to find the barium ion concentration, I'm going to do a little bit of a dilution. Remember, C1V1, C2 is the concentration of barium ions over V2. So I'm going to take my 0.005 moles per liter concentration, multiply that by the volume that was used, which was 20 mils. I don't need to change the volume into liters if I'm doing this calculation because I'm dividing by another volume that is in milliliters. The new volume is 100 mils. And this will allow me to get the barium ion concentration. So I'm going to plug that in my calculator, get a number. I got 1 times 10 to the negative 3. And I guess if I'm keeping, one significant digit makes sense on the concentration, so that's good. Okay, so there's my barium ion concentration. Now I'm going to do the same thing for the carbonate. I want to find the carbonate. Ion concentration. So I'm going to do the same thing. I'm going to look at that comes from the sodium carbonate at this point. So sodium carbonate, Na2CO3, dissociates into 2 sodium ions and carbonate ion. So if I have my carbonate ion, it's a 1-to-1 ratio with the sodium carbonate, so I know that the concentration of carbonate has to equal the concentration of the Na2CO3, right? And that's because we had the 1-to-1 ratio, right? Just like over here, this was because, like, since I have a 1-to-1 ratio, right? If the ratio is different, then I would just apply that there. Now, to actually calculate the carbonate ion, specifically its concentration, we want to do a dilution because we mixed 80 mils of this solution with the 20 mils of the other. So I'm going to take my original 0.001 mole per liter concentration, and I'm going to multiply by 80 mils because I used 80 mils of it, and I divide by the new volume, which was 100 mils. Okay, so I'm going to do the math there, and my carbonate ion solution, my carbonate ion concentration should be times 80 divided by 100, 8 times 10 to the negative 5. Moles per liter. So now I have the concentration of the 2 ions that are involved. And now the last part I need to do then is look at what is the Q value, right? And the Q is set up the same way as KSP. So to make sure I'm going to write my Q value, I'm going to deal with my barium carbonate dissociation. It's always important you show this step. One, so you can get the right ratio of ions to set up your Q calculation properly. And 2, it's just part of your communication piece, right? So, carbonate. So we set it up, it's a 1-to-1 ratio for the ions. As we did before, because these ions are coming from the 2 solutions that are being mixed, they're not coming from the barium carbonate itself. So we are literally just taking these values as is and plugging them in for their concentrations. Now Q is set up the same way KSP would be, so it's the barium ion concentration times the carbonate ion concentration, and both of these components have exponents of 1 because their coefficients are 1 in the equilibrium. And then I'm just going to sub in my values. Hopefully I haven't made any mistakes on the math part. Alright, and so that's going to let us find Q. So I guess that would be 8, I don't need a calculator, 8 times 10 to the negative 8. All right, so I've got my Q value. Now I want to go back and compare to KSP. KSP is 8.1 times 10 to the negative 9. So there's Q. I know that KSP is 8.1 times 10 to the negative 9. So now it's just doing a comparison, right? If I look at these two things, Q is clearly larger than KSP. So this is a scenario where we're going to get a precipitate. Okay. If you are not using Q, you might be using TIP, the trial ion product. So you could use that in place of Q if you want, but either way, it's fine. So that's how we can solve those equilibrium problems relating to KSP and trying to predict a precipitate using our reaction quotient. All right, good luck.